Hello, welcome to the second session on final exam model question paper solutions. We stopped where these two instructions were compared. I explained about push and pop in particular in the last lecture. Let us continue on that question before we go further. If you recall, maybe I will write it again to summarize what has been taught so far so that you have a clear idea of the differences between push, pop, STM and LDM. Okay. Now main difference is push pop depends on only the stack pointer which is pointing at the address. Similar to pop, it also takes the address based on what is being loaded into the stack pointer, which is nothing but R13 or stack pointer. Okay. Now what about STM and RTM? These instructions have a specific base register, and based on that address it operates. So it could be any register Rn that we mention it in the instruction. Now I can give an example of each of those instructions to start with. Now let me write a sample instruction here, push. Then I will give some registers. Let me give R3 and R5 and R1. Okay. Then I pop. Maybe I will put it in the same order, but maybe I'll change it so that you know I'm giving the same set of three registers in this instruction, but when mentioning it I am giving it in a different order. First thing what you should know is whatever may be the order I give, internally the processor is going to look at it from the lower numbered register followed by the higher one and the next. Okay, because it's all encoded as a set of bits inside the instruction, so it will always look from the lower number register to the higher number register, whatever operation it is doing. Similarly here also it will be reordered internally by the processor which is looking into it in this way. So this is very clear. Now let us do the same thing here in STM and LDM. Maybe I will little bit increase the size so that I am here going to give a summary of all this instruction where you will have a very good idea of what is happening here. Now STM, what I do, I have to be specific on one register which is going to have the base address. So let me, in our case, let us take R0 as a register which is holding the address, base address, and then I am going to give a set of registers. So let me give here R5 the same set of registers, but I am just giving it in a different way. So STM is gone into my area of LDM. So let us move over here. Let me erase it in case if you don't like this guy coming here. Okay, now what I am going to do, I am going to give you the LDM instruction also I am going to cover here. Okay, so maybe we'll take this color, LDM instruction. Here also I need to give one base register. Let us assume that I have chosen to give, oh sorry, LDM, right? Okay, now LDM, I'll give base register which is supposed to be here R0, and then I give these three registers the same set of registers. Now let us compare this instruction how they manipulate doing things. Now first thing what we should know is which are writing into the memory, which are reading from the memory. Pushing is writing into the memory. It is pushing something into the memory. So let me show it as this, pushing into the memory. So that means it is writing into the memory, right? Pushing into it memory means writing something from register to register values into memory. Okay. Now what about this pop? It is taking out the value from memory, so it is reading from the memory into some register. What about store? Store is storing into the memory, so it is equivalent to writing into it. And LDM is loading into the register from the memory, so it is reading from it. Okay. So this you should be very clear about operation, what memory operation is each of these instructions are doing. Now all of them are in one way same, that they are all trying to store or read three registers here. Now when I am saying registers, it is implicit that they are all 4-byte values only. It is going to store or restore 4 bytes of values from the memory into register, or storing from register to memory. Now only difference between these is how they operate and how they increment or decrement the addresses in each of those instructions. Okay. So pushes can be many times, many types. I have already explained about push or a stack operation. Either it can point at an empty location or a full location. Either it can decrement or increment. It is true with a push and pop. Whereas store and LDM have a common way of doing things. It does in only one way. There is no other different types possible. Whereas push and pop, there are many possibilities are there. Not many, 4 possibilities are there. But what we have chosen in RP2040, not you and me, it is the ARM or Raspberry Pi guys, have decided to use full descending type as a stack inside the processor. Full descending. That means what? The stack pointer is going to be pointing at a location which is full, and then it is going to, if it is supposed to push something into it, it is going to descend into the stack. That means it's going to go towards the lower address. If it is going to pop, it is going to go up. It is, see, always this full descending or empty ascending, descending means for the push operation. When what you are going to do while writing into the stack. So it is going to be descending. It is going to go towards the lower address when it is pushing something into the stack. So let me now draw the memory. If you are already understood this, you can in fact go faster, but those who have not can listen to it and understand it better. High and low addresses, and stack pointer is pointing at some address. R13 is pointing. Okay, I will be mixing the SP and R13 alternative. And full descending means it's full. Already something is filled. Why am I not showing anything? Because I don't know what was the push instruction earlier done on the stack, and I don't know what value is there. So I am always assuming that the stack pointer is pointing at a location which is already full. The 4-byte values which are there starting from the address, they are having some content which I am not supposed to touch. Now the processor is executing this instruction push, and it wants to push 3 registers in given in this order, but it is internally reordering them in this way, and then it is going to decide how am I going to push it. Now always this is accepted or implemented in such a way that the lower number register is at the lowest address which are possible to be filled in. Now it is already pointing at this location. Maybe I will take the same example of 2000 everywhere. Now because 4 bytes are there, one more important thing I forgot to mention earlier, though I have told, all these addresses that I am looking into either in this RN register or in the stack pointer, okay, or R13, in all the push and pop or STM and LDM, these base registers that I have, they are all filled with an address which is 4-byte aligned. That means the lower 2 bits of those addresses are zeros. That means the addresses will always be incrementing in terms of 4. There is no the initial address, starting address, but it will be filling those locations inside them, but address will always be 4-byte aligned. So when it is decrementing it, it is starting with 2000, which is 4-byte aligned address, 996, 1996, then 1992, and then 1988. These are the 4 addresses which are there. Now which is the lowest address? This is the lowest address. Now which is the lowest register number? This is the lowest number. Now why did I go 3 times down? 3 into 4 times? Because 4 bytes, each of them are going to occupy 4 bytes. So I have to take the address which is 4 values lower than this. And then from here I will be filling 1996, 1997, 1998, and then 1999, then 2000, then that values will go. Within this I will follow the little Indian or big Indian order, how I am going to load the byte, lowest byte or least significant byte or most significant byte, where I am going to put it. That's the NDNS business. We are not going to bother about NDNS now, though it is internally followed. Okay, our aim is now to fill that R1 value here. We are not looking into the way it is filled, but maybe if you are very keen, you should write it in a proper way, because you know that in RP2040 little Indian is followed. So the lowest address is lowest 996, 7 and 8, and so a lower byte, least significant byte will come if it is a little Indian ness is being followed. It's okay. Now which register value will come where? So we need these three locations because three registers have to be pushed into the stack. So, and the convention is R1, the lower number register will be at the lowest address, then the next bigger number, and then next bigger number. So that's it. Done. Push is done. Now imagine the stack pointer, immediately after that push I am performing the pop. So let me assume that the stack pointer is pointing at 1988. Okay, this is the value that SP is having, and then R1 is here, R3 was pushed, R5 was pushed here, and something else was here. Now I need to pop. Now I am popping it into the same location, so it is going to take the lower number register value from the lowest address. So it is going to, so if I have to show here, it is like this, and now if I am showing here, it is going to be like this. Okay, it is reading from this and putting into the register pop, and then the stack will be updated to point at this location, which will come back to 2000, and the R1 value will come here, whatever is stored here will come here, and R5. So that's a pop operation. So I hope this is clear, and how the stack is going to be updated, Now this stack is full descending stack, is a type of the stack. Now in terms of operation, we can also say that for every push operation it is going to decrement it and then push it. Okay, so now let me show a manual which I will also be sharing along with the video. I will put it in the classroom. Now see, we are talking about STM right here. Now STM is called increment after, or no, it is LDM STM, so I am not I will come to this LDM STM. We need to talk about it. The push pop, maybe I'll go. Just let me show you that push. Okay, we are talking about push, right? So let me show the push instruction. Push instruction is here. Let me go here. Now push is here. Push register list, full descending stack. Push stores the register on the stack with the highest numbered register using the highest memory address, and the lowest numbered registers using the lowest memory address, which is clear. Pops loads registers from the stack with the lowest number register using the lowest memory address. That means the content of lowest memory address is pushed into or popped out into the lowest number register, and the highest number register is getting the content of highest memory address. Now push uses the value in the SP register. Okay, it is always default SP. -4 as the highest memory address. Now -4, why is it done? Because it is full descending. So it does -4 because always pushes 4 value. So whatever is 2000, -4 is 1996, which is used as the highest memory address, used for storing the highest number memory. And then based on the number of values pushed, it will go down to the actual content. Okay, I hope by reading the manual also you will be able to appreciate what is happening here. Now let me come back to LDM and STM, which we left out in the last lecture. So let me come here to the manual and go back and come back to, we are looking at the instruction which is STM. So let me look at the STM. Where is it here? STM is here. So let me go here. Before I show you the manual, let me explain it clearly now. Now imagine I am similarly to RM, I am loading, writing into the memory. So let me assume that R0 is having 2000. Okay, same, okay, decimal value. So memory is here. So little bit I have to show you in a different way. I'm going to show that R2000 is here and R0 is pointing at this address. Okay. Now imagine always the STM and LDM are used for array of values, no data array that you have declared, and now internally the you are actually trying to store the content of R5, R1, R3, but it is internally changed into this order. Okay. Now where does this values go? Okay. What happens is whatever memory it is pointing at, it's always going to write from that onwards to the high addresses. Okay, please. This is always, it is independent of whatever being followed for the push and pop. That's why I want you to keep an idea that push and pop are specific to the full descending, whereas STM and LDM are always follows one standard way of doing. This may be a empty descending, full descending, or empty ascending, full ascending. Stack can be anything. Whereas STM LDM follows the same method, because how you are going to manipulate arrays, always when you are declaring an inter array of 10 integer values, a of 0 is going to be at the lowest address and a of 9 is going to be at the highest address. It's not going to be changing. Array is going to be always starting from lower to higher addresses. That's why always remember when I'm loading or storing a series of values into the memory, we are not using the stack. It is the data area. Please remember, both are different. They are operating, this instruction are operating on stack area of the memory, whereas LDM, STM are operating on the data area of the memory. Maybe you may make the R0 to point to the same location where the stack is. That's again, internally you are implementing it, but you are not going to operate it as a stack. So it is in the increasing address. That means the lowest address is 2000. Next to 4 addresses 2004, 2008, and 2012. Now, which are the addresses it is going to use it? It is going to use the location which is already pointed by 2000. It's not going to leave this empty. Here, whereas stack pointer, if it is pointing here, it is not going to use that value. It is going to go down and then trying to do it. It's because we are following full descending. So you have to keep your mind away from the stack operation and always think as a STM as a separate instruction which is independent of stack. It is nothing to do with the stack. Maybe I can have R13 here, but I don't. I will not give any problems like this. So assume that it's not R13, it's R0, and it is a data area. And what will go where? R1 will come here, the lowest memory address. Next higher address is 2004, so R3 will come here and R5 will come here. Now, if I am updating the R0, okay, if there is a getting updated, exclamation mark is there, but I am not planning to give any exclamation mark in the exam. So, but I'm just explaining it for you to have an idea. It has to be incremented to point at an empty location. Okay, that means I already filled these locations and I will increment it by 12 and then it will be pointing at an empty location. So it is always going up like this. Now, what about LDM? LDM is going to be like this. So let us assume that I was having earlier 2000 this address. Now I had put R1 here, R3 here and R5 here, and I am making it point here. Okay. Now I want to load from this address. Now what you need to do here is you will be giving the address where the first location is here. Okay, it's always the same address is given. It's not that you are giving some different address. You are giving the same address 2000 here. Here also you are giving 2000 and then asking it to load from the memory into the register. Now what does it do? The lowest memory address content will come to R1. Then this arrow mark is like this. Okay, whereas STM is from the register to memory. Okay, so like this it goes. So here what happens is R0 is pointing at the location where the first data is. Always it is going from the lower address and then it will increment it. Okay, it's nothing like reverse is done in LDM and STM, whereas in push and pop it will be reversal of things. Okay, you one in one place when you are pushing, you may be decrementing it, and pop you will do the reverse. Whereas in LDM STM you will do the same thing in both the cases, but the lower address will be having the lower register number. Okay, the value which will be taken out from there. So what is that you need to write? Okay, the question is a simple question which is one more question here. You need to write STM uses stack pointer and maybe example you give and then draw the picture. That is enough. You know, push and push uses stack pointer and STM doesn't use, and based on the register you are base register you are giving, it will be uploading it, writing into the storing it into the memory. And push always uses in RP2040 full descending mode. In that case, stack pointer will be used as an implicit base register, and then how does it operate on the memory. Okay, that's all. Both are writing into the memory, and pop is reading from the memory. Okay, I think I have explained both question 5 and question 6 in one go in this explanation. Okay, I hope it is clear to you. Please ask me in case you still have any doubt. But listen to this lecture again, and then I will be sharing this manual also. Read it. It also says something, and maybe I will explain you shortly here. We call LDM as increment after. Okay, what does it mean? I will explain here. Okay, here LDM. Okay, let me use a different pen because I am writing something into it. So let me use this. LDM is also called LDM increment after. That means what? You are loading. Suppose now I told you that LDM is R0 is pointing at 2000. You are going to load this value into R1, and then you are going to increment it. Increment by 4 after loading this value into the R1, and then you are going to take the R3, then you are going to increment it to 2008. You understood what is LDM increment after? That's it. Now what about this STM? It says STM also increment after. I am ignoring this E and A FD for a while. I will also explain it, but if you don't understand, it's okay. But for the completeness sake, I will explain that. Now STM also STM increment after. Now what does that mean? I told you that R0 is pointing at the empty location. That means you are storing the R1 value into this, and then you are going to increment it after that, and you are going to load the R3 and R4. So it is also increment after. LDM is also increment after. That means they are both are moving in the same direction. Okay. Now there is one more related to the stack. Okay. Again, they are mixing up the stack just because stack also can do the same thing. In case if stack is doing the same thing, what it would be called as. Okay, that's what. Please don't mix this with the stack pointer, but you if you go deeper into different ARM architecture, you will come across this. So it is not part of the syllabus. I'm not going to mention about FD and EA, but for the completeness sake I am saying it, and those who are interested in going further into ARM architectures and want to understand it, this will be useful. Now let me explain. LDM IA is also same as LDM FD. So let me tell you that what is that LDM FD means. Okay, so let me use a different color to bring out blue. I'll use this color. Okay, now what is LDM? LDM I am going to, it is saying that LDM FD. Okay, now what is LDM FD? FD is nothing but full descending stack. In case if it is a stack operation, it is a full descending stack. Now is it so really? Okay, that's what we have to see whether it is similar to full descending stack or not. Now LDM is taking from the memory, and we are assuming that it is pointing at a full value. That means it is already having a value, and then it is similar to LDM FD. Okay, Now, so if it is equivalent to a stack operation, it is full descending. Okay. If you don't understand it, it's not a crime. Okay, it's okay. But I will, completeness sake, I'm going to explain this now. It is equivalent to popping. Okay, because you are loading from the memory into the register, and if it is a stack operation, it is going to now shrink. Stack is going to shrink. Now, descending means stack is growing towards the lower address, right? When during the push, if the stack is growing towards the lower address, it is descending, and if it is pointing at a full location, then it is a full descending, or if it is an empty location, it is a empty descending. Now, if it was a full descending stack, assume, okay, now it will be pointing at the stack pointer, must be pointing at the location which is already full. Okay, that means this is the address where it is going to be pointing at. If earlier I have pushed R1, R3, R5, it would have been like this. Now, when I am popping it, I am doing a LDM operation which is equal to pop operation. So, it will be going towards the higher address. The stack will be going, sorry, this is push. Okay. Now, pop operation is happening and the stack will be going towards the higher address, because if it is going towards the lower address, it is descending. Because I am doing a pop operation, you should go towards the higher address. Now, what does it do? The lowest address which is having currently SP is pointing at 2000, suppose, then R1 will go to R1 value will be copied from here 2000, then R3 and R5, and then it will be pointing at some location where the stack is already full. So it is a full descending stack. Is that's why the another way, another name for that is LDM FD. Okay. Now, very interesting stuff. Now, STM IA, I told you that it is always STM is like this, but why is it called STM EA, empty ascending? Okay. So, let me talk about that. Okay. As a completeness sake, I am doing it. Please remember empty ascending. Now, imagine again, this is a stack pointer. Okay. And I am doing a push operation. Okay. I am doing a push operation, and the address stack pointer is again pointing at 2000. Now it's called empty ascending. That means the stack is currently pointing at the empty location. So I can actually push R1 into the location where I am pointing at, and then R3 and R5, and then I will update the stack to point at a empty location. And I am going towards a higher address, ascending, and I am pointing at the empty location. So it's empty ascending. It is equivalent to a stack operating as an empty ascending. Okay, this STM operates like a empty ascending stack. That's all it says. Okay, this is very little tricky, but if you get it, actually you will enjoy what actually this manual says. Because I'm going to share this manual, I thought I will write about this, I will talk about it. It's not very important that you should know it. Okay, fine. Now, I think I have completed everything about LDM, STM and push pop. I'm not going to cover it again. Now let us look at the other questions that we have. I think these two are done. Now again STM R3 is coming, which is what happens when the below instruction is executed. So let me copy this guy. Very simple. You can pause it and write it yourself. Okay. I'm sure you will be able to understand this very well. Even for completeness sake, I will talk about it. Now imagine, let me change the color. I like this. Okay, again memory. Okay, I have to point it to something because it is going to be always going towards a higher address STM. It is storing something where R3 is pointing at. It could be some address plus 4 you will do. Okay, and imagine it is a empty location is pointing at STM, and I will write R1 here, sorry, R0 here because this is the lowest result. So I have to rewrite it into R0, R1, R2, R5. Okay, that's it. and then try writing it. Okay, and did I mention? I have not mentioned anything, any specific value. So you can mention that 4 bytes wide. Okay, that is important, and then say that it is storing it. So you can put an arrow like this. That is enough. A picture talks volumes of information. Okay, than writing few words. But I want you to write a few words also, that internally these registers are ordered in terms of lower numbered one first and the higher numbered register later, and then wherever the R3 is pointing at, that location R0 will be loaded, and then plus 4 will be done, and it is going to load the R1, R2, R5. Because I have not given any specific address, so you can write it like this, or you can assume some address 1000 and then say the next location will be 1004, 1008. I leave it to your imagination. Okay, this is what you are supposed to do for this instruction. Okay, that's very simple. You are all experts now in LDM STM. Give one use case scenario of DMA with example. Now DMA is going to be covered in a very detail in the later question also. Here I am going to just talk about a small simple example. If you recall, I told that core 0 is sitting here at the top as a master, and then the DMA two ports are there. DMA is two ports. Let me extend this DMA. Okay, one is writing. Okay, means there is two ports are there. These are all master ports. This is a light. Okay, ASB light fabric, and then we have 10 slaves. Okay, that SRAMs are there, and then it goes to flash. ROM is there, similar SRAMs, and then it also goes to peripherals. Okay, now what is this AHB light fabric? It is going to connect these cores or DMA into any of these places. Now, what does the DMA do? Direct memory access. It is programmed by the CPU. Okay, you don't need to draw this picture. I am just drawing it to give you an idea of how things really happen. So the core 0, core 1 right into the DMA. Okay, and says that, okay, there are two ports connected. So this is don't think that there are two DMAs are there. This the same module DMA has a two ports connected to the fabric, so that if suppose you are programming the DMA, what is DMA? We want the DMA to do some job, on behalf of the CPU. Okay, CPU says that, hey DMA, why don't you do something? I want you to, maybe this is a SRAM. Okay, let us assume this is some peripheral, maybe UART. Okay, in some location I want you to copy this byte. Okay, read it from here and write it into the UART. So the UART will send it through serial port. Okay, okay, we will come talk about the serial port soon. It will send it out through serial port. So I want this bytes to be read and sent to it, but I don't want the CPU to be involved. Now what happens, SRAM is a memory, so so many bytes are there. I read byte by byte. Okay, from some address, maybe I will say 500, and then I keep reading that byte 500, 501, 502, and then write into this UART, and UART will send it to other device which is connected to it on a serial port. So this is one way of communication. So one use case scenario what we can show is DMA is reading from it and CPU is programming it, what short address you have to write, and then end address is, it would be a UART address which is FIFO. Then it will be writing into it, and then the data will go out. So it will be incrementing on this side. It need not be incremented here, but what you can do is you can say that it is data is read from one memory to another peripheral, or it could be another memory to memory also. It's very simple for you. You can say that copy from location 500 to 2000. That means 500 by whatever is there at the location 500 will come to 2000, and then 501 will come to 2001, so on. So you have to mention how many bytes. So sir, maybe 100 bytes. If you say 100 bytes from 500 up to 599 is read and then written into 299, something like that. Okay, 2099. So from 2000 onwards. So we can explain one scenario of memory to memory transfer, or memory to peripheral, or peripheral to peripheral, or peripheral to memory. What these three combinations you can explain. Okay, so that's what I want you to do it in this question. Very simple explanation. I don't want you to elaborate for 2 3 pages. Just a few lines. Crux of the things you should bring it out. Now, what is I squared C, and explain the functionality with one use case scenario. So, I squared C means what I can tell you is a inter-integrated circuit. Okay, maybe what you can do, imagine I squared C I2C of a device. You can write it pi 40. Okay, RP2040. Okay, one device. Maybe you draw another RP2040 which is having I squared C. If you are very imaginative, we can even say ESP32. No problem. ESP32 also has your I squared C. What I want to is, maybe I will rephrase the sentence or a question to say that show the connection between this. Okay, show the connection between I squared C blocks. Now, in the lab, I have already told you that ground is important, though video doesn't bring out that. Please remember, ground is also important for I2C, connecting two different devices on two different laptops. Okay, if suppose they are not on the same laptop, you need to have a ground connected. So please mention that. And then, what are those two signals? You should know this SDA and SCL, serial data, and then serial clock. So what about on this side? It is the same SDA and SCL. So you don't need to show the pin number or anything. I don't want you to memorize anything. Just say that SDA is going to SDA of another device, SCL to SCL. It could be I squared C 0 here, I squared C 1 here, or whatever, or it could be ESP32, or maybe Arduino. Arduino also has Arduino, ESP32, I squared C bus, or you can also mention another Raspberry Pi Pico, okay, RP2040, two devices, and you can connect them. So I may ask you to draw the circuit diagram how you will connect two different devices on I2C bus, and then one scenario. Maybe what you can do is, this is the master device and this is the slave device. You can give some address, maybe your own USN number, and then master sends the data to this particular slave device, and it goes into this, and master drives the clock on SCL. You can show a clock diagram, and then the data flowing from master to slave. Okay, if it is writing into the slave device, suppose slave is sending the data out, the data can be shown as leaks, and the master is reading from the slave. So it says slave device 21, please send the data. Then it puts the clock, master drives the clock, and the data is driven by the slave, and it is read by the master. So either this way you can write it. Okay, mention the master, slave device, and the flow of data between master to slave or slave to master. Clock is always driven by the master. That means it is putting the clock, and then slave device response. Okay, a particular slave device will be shown. Now, if you are very imaginative, you can also show on the same line other devices. Multiple devices can be connected also. Another I squared C can be connected, where it can be having another slave number on the same I squared C network. That's it. Okay. So show a simple diagram which is and then explain it in one word. That's it. Now, what is the significance of baud rate in your device? Very simple. I have already explained it to you. Maybe I will explain it in the context of laptop connected to the board, which is you are supposed to know. Okay, this is the RP2040 board. You are connecting always this, and then you might have also seen the serial monitor. Please remember, whatever you did in the lab is going to be very useful. And then there is a baud rate which is shown here, maybe in the top, I think. So it says that you have to choose some baud rate, right? If you drop down menu, if you see in the Arduino IDE, you will see that there are different baud rates given. Now, you are also writing a serial dot begin here, which I asked you in one of the questions. You mentioned the 9600 baud rate. Now, if you mention this 9600 on serial begin, that means you are programming this this port, which is on the USB port, a serial port running on serial protocol running on USB physical port, having a baud rate of 9600. Then the serial monitor also should be chosen as 9600. Now, what is the significance? You can say that if two devices are communicating over serial port, okay, the signals are TXD on one side and RXD on the other side, and then RXD here, TXD here. So that's the difference between a UART device and the I2C device. Okay, both are UART device. This also UART. It could be two different devices, or it could be same devices, UART 0 and UART 1. Now ground should be there. Okay, for sure ground is there, and you don't need to give the pin number, but only show that TXD is connected to RXD, RXD is connected to a TXD. Okay, this is TXD and this is ground. Ground is connected to ground. So how does the data flow? Any data going from this device goes in PXD like this, and then any device coming from the other goes to through the RSD, and you can show the data flow on the bus is like this. Okay, three lines here also. I can see also three lines. Only difference is you can't show another device connected to this. Only it's a one-to-one connection between two devices. Only I port can be connected. So that's all you have to say. And then the significance of baud rate is the speed with which the data is sent on the serial line has to be no, the configuration on both sides should be the same. Then only this device will be able to understand what is being sent by the other one. Okay, suppose if you are not able to follow the speed with which I speak, then you slow down at the rate you can understand, and then you start observing it. So unless the receiver is aligned with the speed with which the master or the slave the transmitter is sending, they won't be able to read it, right? Suppose if you are not able to understand uh, the way the speed with which I speak, you slow down to the level you can understand, so that you can follow it. Same way, if you are saying programming it for 9600, this also should be 9600. If it is 115200, this should also be 115200. Maybe you can explain it in your own words that the baud rate should be fixed on both the TX and RXC side, both the devices, your devices, so that when any device communicate with the other device, if this is sending something or the other device is sending something, they will be received without any errors. Okay, that's all you need to explain. So with this, I am completing the part A explanation. So let us come back on the next lecture to talk about the